there.
So,
All right,
oh yeah.
I'm going to go ahead and start up. So last time I was talking about the current steering circuit, right? And I threw it up on the board and couldn't remember if it was the right way or not. And for some other reason, I was playing around with it. So this is we use an AC signal, but there's two practical applications to this. One is I can make a plug here, and I can accidentally plug my thing in backwards, and I'll still get positive voltage out, and it won't blow things up. But from the point of view of so if I put a positive voltage here and a negative voltage here, I get a current flow. Remember, we talked about diodes being one-way valves. I get a current flow that goes through this one and out, and then back in and back. So I've got a source to my battery, right? So that's if the battery's hooked up this way. And then if the battery's hooked up this way, negative to positive, then I get a current flow that goes that way. Now look at this.
It doesn't go up because don't you have the little half loop?
I've lost myself.
Yeah.
I've lost it. I've lost it. I've lost it. Current goes. Oh, there we go. I drew the wrong track.
Yeah, so that's not connected.
Yeah. Current goes this way.
Yep.
There we go. Sorry. And then it comes back
Yep.
that way.
Correct.
That way. So no matter what I do, I'm always positive. So her question just a little bit ago was, well, okay, that's great. Oh, but you also lose 0.7 volts there, and you lose 0.7 volts on each one of these. So if this was 10 volts here, I'd be at 8.6 volts out here. So
That's what the diodes.
yeah. Now there's things you can. There are some very clever circuits out there where they use transistors and they use voltage sensing, and it sits there and turns them on and off at the right phases so that you get everything through.
Okay.
And they get rid of a lot of the power losses of this. I'm not going to go into that because that's
Okay.
actually a fairly complex circuit that requires a completely separate power supply to run it.
Don't really understand the basics of circuitry.
That's fine.
That's
Yeah.
fine. We'll get back.
Yeah.
These represent wires. Any line represents a wire.
Oh.
So a wire telling a lie has no resistance. It works like it carries current from point A to point B
Without any
Loss.
without any loss.
Yeah.
That's a lie. The truth is that's not true. But
Some of the components, yeah, there's but it's minimal.
so now we get into the okay, practical use. It's the way we used to make power supplies all the time for off of the wall. We talked about inductors and putting them together to make a transformer. So what happens here? The AC is going off the wall. This is 60 times a second, plus minus, plus minus. It's a sine wave here that looks
circuit looks a little incomplete.
like that. And so we talked about the magnetic flux coupling between these two coils. And as the current increases through this one, the magnetic field expands across this one, induces a current in it. Because it's a 10-to-1, it's a 10-to-1 knockdown. So now instead of 120 volts AC, I've got 12 volts AC right here. But now we play the same game, right? So this is effectively positive. This is positive voltage, and that's negative voltage. So this thing's doing what I drew over there. Now what I get at this point right here looks like this. And it's 12 minus 1.4, so 10.6, right? 10.6 volts here. I run it through a capacitor. Now I get, I'm going to draw this again, and then I've got my load out here, whatever my load is. And so
So that becomes DC.
it becomes sort of DC, so we would call this 10.6 volt DC, but it has a ripple spec
It's
here.
DC.
Direct current as opposed to alternating current. And
So it
so
says
It's always positive or always negative.
Right.
it's stagnant.
it's not stagnant. What it means is that the current is only running a single direction.
Oh, so normal currents just run both.
Well, so we have
So that's why they call it direct.
yeah. One
One direction.
you don't have a sign change. It's always running the same
So
way.
what are the advantages for direct current?
Well, almost everything we use is DC actually.
Because it keeps most of the power constant.
No, it's
It has to do with when you get down to the circuitry. So we're going to get there. So let's go ahead and get there. Last week, refresher. Last week we talked about the diodes. We talked a little bit about inductors and capacitors and resistors because that was the refresher from the week before. We got into semiconductors. We talked primarily about diodes. We had LEDs, Schottky diodes, Zener diodes, tunnel diodes, Shockley diodes, and general purpose diodes, which for the general purposes, we're mostly going to use general purpose diodes. Actually, we're mostly going to use light emitting diodes, which are a general purpose diode that gives off light. Otherwise, they act pretty much the same. So there's one other, so we get into transistors, and this will be a very good reason about DC. So we'll start with a bipolar junction transistor, BJT, and there are two basic styles. There's an N-type and a P-type. An N-type, this is the symbol, this is the base, this is the emitter, and this is the collector. Base, emitter, collector. And this arrow is important. That's what tells me that this is an NPN. NPN as opposed to a PNP. Those letters tell me about the doping of the three legs. It's actually a drawing of the physical semiconductor inside, sort of. What this guy does is I have I base, I emitter, and I collector. So I have I is current.
So it goes down.
Current flows this way.
Yeah, because I am collector and I am emitter, kind of obvious.
I emitter is equal to I collector plus I base. It's probably my son. Yeah, it's my son. I gotta hang up on him. He knows I'm doing this tonight. Emitter is equal to collector plus base, and IC is equal to beta IB. Beta is also known as HFE. Sorry, Adam, I gotta hang up on you tonight. This is a gain. It's a gain factor. And if you buy just you've got a pile of transistors in there, and if you look at them, they'll have a beta. And beta, most of the ones you'll buy are probably around 100, but you have to be careful when you do a transistor circuit.
So you don't screw it up with static electricity.
That too. Static will blow them up, but their beta can be huge. Beta for probably one of those runs anywhere from like 50 to 200. So that's a huge difference in gain. So when you're doing analog circuits, we're using this as an amplifier. You've got to be very careful about your design because temperature things come in and different different transistors will do different, so you want to make a design that's independent of beta.
This is a semiconductor circuit.
That is a semiconductor by itself.
Oh, so
A single diode.
that is expensive for simple.
Well, you can buy these days for 20 cents.
No, what was the 50 to 200?
That's the gain factor. So what
Oh.
you'll normally do...
That's just like an increase, a step increase. But
Yeah, in the simplest sense, you can take this thing and you can say, this is a load resistor here, and you take an output there, with this being your ground. So we talked about this earlier. Every circuit needs a reference point, and we call ground our reference. So if I've got a battery over here, I'll call this V whatever, VCC for all intents and purposes, and I'll have a ground. And then current flows in and back through this ground. So the symbol, now I don't have to draw the whole underside of this, I just know, oh, it went back to ground. So what we'll say is, let's say this is our 10 volts from earlier, 10.6, I'll call it 10. And you'll say, I want this to be 5 volts. So we go back to R, and this voltage drop right here is 0.7. Remember Kirchhoff's laws, current law, are the voltage loops and the currents into the nodes, right? They'll have to add up to 0 or be equal depending on which. And I'll say when this thing is all the way on, this voltage is about 0.3 volts. So, but I know that if I want 5 volts there, that means there's a 5 volt voltage drop here, right?
so it has to go somewhere.
So we know V equals IR, and we know we have 5 volts being lost here, so 5 equals to IR. And we want, let's choose I to be something not big,
1.
1 milliamp,
Yeah.
0.001. One's a gob. So we say 5 is equal to 0.001 R. Do the math, R equals 5K. So now we've got a 5K ohm resistor here. And now I know that my normal current here is 1 milliamp. And if beta is equal to, we'll call it 100, beta equal 100. And we know that IC equals beta IB. So 1 milliamp divided by 100 is 10 microamps, right? So I want to put 10 microamps in there, and that'll bias this. So now I can say, oh, I'll put a resistor here to protect the front end. And I can put in, I can do all the math to figure out what this voltage out here needs to be. And that can be, remember we talked about a voltage divider circuit. We can get there in a couple of different ways, self-biasing, whatever. But let's do this. Let's take this guy up here. This is a bad circuit to our 10 volt rail. And I know this needs to be 10 microamps. So now I've got
A short up circuit.
I've got 10 volts minus 0.7, 0.7 equals
9.
RB equals 10 microamps times RB, right? No, equals 0. IR, 10 micro RB,
0.9.
10 minus 10 micro RB. And I've quickly, that's 9.3 and equals 0. So now I move that to here. And I take 9.3 divided by 10 micro equals RB. And that's 993K or 930K?
What was that?
I don't know how much a micro.
Micro is 10 to the minus 6.
Yeah. So that is
9.3 times 10 to the.
but divided by 0.00001, 930K. So now RB is 930K ohms. Now, this thing's running, I got 5 volts here. Put a capacitor in line. I hook up that electret mic that's putting out a tiny little bit of voltage. Remember one of the things that capacitors do? They block DC. So my electret microphone, my microphone is over here. I don't remember what the symbol for a microphone is, so I'm just going to say mic. Connected like this. Now when I talk, there's this little bitty thing here, but that's current.
It's not going through.
The DC is blocked. The AC, which is our voice signal, which is constantly oscillating, goes right on through here, and now I get this beta of 100 gain on that. So if this was 1 millivolt here, now I've got 100 millivolts there. Which isn't a lot, but a couple of stages of these and you can really amplify a signal. That's how a loudspeaker works. That's how the speakers are.
Probably be really quiet if you're talking to them. Like
electrets put out crap for signal. I think an electret is, I think it's about plus or minus 0.1 volts. That's what you see out. But multiply that times 100, and I'll saturate this thing. It'll blow up. Now it won't. This circuit here is bad for driving a load. I'll tell you a bunch of
too
stuff.
much.
It's not. The impedances aren't matched right. You'll lose most of your energy right there instead of delivering it to your load. This has bad temperature sensitivity.
So overheat.
It won't overheat, but as the temperature changes in the room, its performance is going to change.
So it's going to be.
And it's also got bad beta sensitivity. If I pull this one out and it was a 100, but I grab another one and put one in and it was a 200, now it's going to clip my signal for the same signal, or if I put one in that's a 50, it's not going to give me enough signal out. So there's a lot of things to do with a transistor circuit to make it a good circuit. But for what we're going to do in the maker world, most of this probably doesn't matter. But that's how it works. What we're going to do in the maker world is, the other type is the PNP. Looks like this. PNP. Collector, base, emitter. Remember the other one was hooked up this way. Whoops, that's not an N. P, N. Notice the difference. Current flows this way through a P style. Current flows this way through an N style. They each have their uses, but if you're using AC, current's not going to flow if it's one way, but it will flow.
What is that, transistor?
This is a bipolar junction transistor.
Okay, and all you're doing is.
This is a PNP. This is an NPN.
So all you're doing is redirecting current.
Right. The way to thinking of it in fluid.
Right.
If it was water.
Yeah.
Think about it as
like a T pipe or a T connector.
It's not even that. Think about a ball valve. So water can only flow this direction.
Right.
Water can't flow that way, but let's say that the normal water isn't quite enough to push that ball out of the way.
Right.
So now you've got a little pipe that comes in this way, and this little pipe is just enough to push that ball back and let water flow.
Okay. So it's like a helper.
Yeah.
So basically, but what if the little ball gets stuck in there without that little pipe? It's gonna
Then you don't
rupture.
need you don't need the other.
Well, so from your point is, I can put too much voltage on this, I can put the voltage in the wrong way, really badly, and it'll break the pipe.
Okay.
I can burn
Not
it.
sure.
But the same thing with a transistor, right?
Yeah, that's what I'm getting at. If I put the voltage in the wrong way, I can blow my transistor up.
Okay.
It's not water, it's not really a pipe. This is nothing at all like what the actual physics are that are going on inside of there.
But it basically bursts or breaks.
Yeah, you'll blow it.
Yeah.
So if you put AC on this, you can damage your circuit. You can damage this thing. Now, what we'll use these for is switches. We'll bang them hard. Instead of putting all the protection and whatever on the front, usually that I was talking about, we will use our microcontroller and we'll put a little resistor there just to protect everything. And boy, we'll bang that guy. Bang, 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 bang. On, off, on, off. On, really on.
Yeah.
If you look at the curve,
On for a few seconds and then it blows out.
no, depends on what you're doing. Depends on what you're doing, and it depends on the transistor. There's transistors that are as big as my fist. I'm not going to blow them up with anything in this room, right? The curve looks like this. Now think about this.
Like a L.
Oh God, it's been a while since I've done this. I got to think about it. The current. This is the current through this thing. It comes up like this. So this is I sub C, and this is
The T.
VB, and then each one of these, there's a set of characteristic curves. And then this is actually VBE, and this is the current. Oh yeah, that's it. VCE, I think. VCE. I know I've got these wrong. It's been a long time since I've looked at these, but there's a set of characteristic curves. The more voltage, the bigger the voltage is here, the more current you can get through. The bigger the voltage is there, the more current you can get through. And when you play these games, what you see is there's a transition time where it's turning on and it's basically off. And then you're here in what we call the ohmic region, where it kind of acts like a resistor, a variable resistor. And then you're out here where it's basically full on and it's not going to get any more on. So in digital circuits, we're basically ignoring this and we're driving VBE way over here somewhere or way over here somewhere, so it's all the way off or it's all the way on. This will become important later. I'm going to switch real quick to a different kind of transistor. This is called a FET, specifically a metal oxide semiconductor field effect transistor, a MOSFET. Their symbol is this. You see a lot of symbols for the same thing. I'm going to stick with this one because this is the simplest one, N-type MOSFET, and a P-type.
I think I recognize these. These are what are used in computers and types in people.
Bingo. So these are nice. Number one, they don't have the leakage through. And they're drawn this way to show that specifically there's no path for current to go through, at least at DC. And we talked about our inverter before, a couple of sessions ago. If I use 5 volts and ground, and if I say a 0 equals 0 volts and a digital 1 equals 5 volts, I put a 1 here, I get a 0 out. I put a 0 here, I get a 1 out. It inverts the signal. So if I put 5 volts in, I get 0 volts out. If I put 0 volts in, I get 5 volts out. This is the basic
Binary.
basic binary, zeros and ones. This circuit inside of your computer is this.
5 volt.
That's it. There's 2 transistors to do that. When we start getting to all the different stuff, it's more complex sets of gates for your different logics, your ANDs, your ORs, your NORs, your exclusive ORs. We're not going to go into that because I think you guys don't care. If you do want me to do a class on that, I will, but I don't think you're going to care much. So what we'll see here is this. So this is your basic input, and this would be just a buffer stage. Maybe there might be 2 of these inside. So on the input to your microcontroller, when you want to put a signal in, it's probably got something like this going on the input.
One thing only goes in, one thing stays out.
Right, but they'll also do this. This is not always important, but sometimes it is.
Where do you usually see these?
This is down inside. This isn't something that you physically see, but it's there. And what this is for, these are called protection diodes on the front end. This is what protects it from static.
Oh.
When you walk around and you've got a little bit of charge on you and you grab this, it lets excess current flow this
So
way.
it's kind of like a little water.
Shouldn't it go to the ground?
Actually, yeah, it should go this way.
So it's kind of like little
No, it
pumps.
Oh, no.
That's right. That's right.
Oh, okay. I thought it would go
Because
to
this
the
isn't
ground.
going to conduct until I get to 5.7 volts on here, right?
So
Because there's a 0.7. If it's conducting, it's plus or minus 0.7 volts, which means this has to be at 5.7 volts. And for this to conduct, you have to be at negative 0.7 volts.
Oh, okay.
because it's a negative charge.
So these are strictly protection. You've got these on your inputs and your outputs. So you notice anything that's in my range, these aren't going to really conduct and they're not going to be a problem.
Good. So now I know that there's a little bit of protection.
There is a little bit of
for
protection.
static on the
You really,
Yeah, but,
well, if you see an arc fly, it's toast.
Yeah, but if you have a
little band.
band,
The wrist strap.
is that exactly similar to that?
Well, the wrist strap, you've got a workbench,
Right.
and what you've got is a connection to you
And ground.
through a big resistor to your wrist here, and and then this is usually grounded back here. So everything on here is grounded, and you don't want this to be a direct ground because if you grab hold of a
Yeah, you complete a
piece of heat,
circuit.
you complete a circuit and
Yeah.
kill yourself. But this is enough to constantly be bleeding the charge off
Okay.
of you so that you don't zap things.
Oh, but
That's why the little bags that those were in,
Yeah.
those are anti-static bags.
so
They're
I'm
conductive
assuming
coating
that
outside.
you can build something with a diode. I don't know if you can do that. If you
Yeah, I
build
think-
something with a diode too.
Yeah, I think people assume anti-static bags are insulating, but they're really conducting.
They're really conductive.
Yeah.
I mean, they're kind of both,
Yeah.
right? But
The idea is to wick away static.
so this matters in some cases because they do have an effect on your circuit. When you're doing digital, which is most of what we're gonna do, no noticeable effect. But in some analog cases, you'll see it. And it does matter because our microcontrollers have analog to digital converters on them. For the most part, it still doesn't matter because you're staying within those ranges, but sometimes you get some weirdness, and if you're wondering what that weirdness is, maybe think about this could do it.
Maybe that's being a little overwhelmed. Was it?
So the P-type here is sort of like a PNP. The N-type is like an NPN. This one connects it's called a gate, source and drain, gate, and source. The source connects to the source. The drain is the same as a collector. That's where you drain current. So it goes through the drain first, and then the gate is the control voltage. Whereas the BJTs were purely current controlled, right? If you remember, IC was equal to beta IB. These are voltage controlled. IDS, drain to source, is equal to the, been a while. VGS minus VT K square root, I think. And K is some constant, and VGS is this, and VT is usually, VT, depending on the transistors, about 1.2 volts maybe for a big transistor. So that means that thing's not going to turn on until this gets up to bigger than 1.2 volts. Then he'll turn on, and he's the reverse because it's up this way. If you have a low voltage, he's off and he's on. If you have a high voltage, he's off and he's on. So you're steering current back and forth between them actively. So let's talk. Is this a good point to go into our microcontroller now?
Do you have one for show and tell by any chance? Or
Well, she's got hers in her box down there.
okay.
So for this, I'm going to stick with the Atmel microcontrollers. I'm going to stick primarily with. I think the easiest thing to do is an Arduino.
Yeah,
Because I can pick up an Arduino board for sub $25.
Mm-hmm.
And I can pick up the inventor's kit like you got there for $100, and
next time.
have all the little toys and things
Yeah.
that connect.
I have to keep.
We have two of them for his experiments.
Yeah,
so-
I've got several of them laying
The
around. in different
website
places.
changed actually.
Oh, really?
Yeah, the actual
Programming portion?
both
Oh.
circuitry.
So well, I'll stick with those because it's publicly available. It's well supported. You can find information everywhere. So the website I believe is Arduino.cc. If you go there, you can download the compiler. Their compiler uses GNU C compiler (GCC) as the back end. They do some funky stuff up front. Yeah, that'll work because that will be done.
Probably missing some parts on the Arduino. Probably lost some like previous classes I've taken.
So
too.
I think what I'm going to do is we'll start to go into the generic microcontroller. We'll talk about it in terms of the Arduino because that's what we'll use, and we'll use their software tools. But this is all directly relatable to any microcontroller, even a computer. If you find the right software, it's hard on PCs and Macs to be able to drive direct ports. They've taken that away, and you can't go out and talk directly to hardware anymore. At least since Windows
3.
Vista.
Yeah, I could do it in Windows 95.
Well,
Windows 95, I could talk directly to a parallel port. Windows, what was the next one? 97?
No, well,
XP.
there was 98, and then
Yeah,
XP.
98 was awful.
No, I think with Vista and NT, before the Vista is based on the NT core, and that's when they really started removing you from hardware
I think
access.
in Windows XP, they pulled the parallel port into ring 0. Or one of the rings that was not a user access ring.
Well, I wish I could use Windows 95 on my little.
You don't need it. Everything works on the latest version of Windows. And it doesn't work too bad. So what we're going to talk about first is you have a core. So we'll call this an instruction processor, an instruction core. And it has an arithmetic unit in it, so it can multiply, well, it can add and subtract.
multiply.
It can't really multiply. a multiply successive
additions.
addition, right?
Yeah.
It can't really divide. That's sort of a successive addition also, or successive subtraction. Not gonna. And
Yeah,
there's no
yeah.
reason to get into the real gooey details. It can do logic operations. It can do ands, ors,
If,
exclusive ors. It can do comparisons.
what about ifs?
That's a comparison.
Yeah.
And then outside of this is a bus. And the bus connects, so you got two sets of things. You got an address bus. And by the way, this is true of the CPU on your
Computer.
your Pentium or Core i7 or whatever. We're super simplifying things, but this is a basic. I think it's called the Harvard architecture. How it works. You've got an address bus, and you've got a data bus.
Isn't that the von Neumann?
I guess there's von Neumann and there's Harvard architectures. I think one of them has to do with how you partition the memory, whether you have a separate data memory from your instruction memory, and then the other one has to do with the bus architecture itself. And I don't remember. It's not been important enough to me to know the difference, to remember the difference. So what I've got on my address bus is I've got a bunch of peripherals. I've got a big chunk of memory over here.
So it's part of the memory.
Well, so what I can do is my address bus can be it's all digital, right? So it's some number of bits. Let's just say that I've got 4 things, 1, 2, 3, 4. What I can do is I can have an address that's 4 bits, actually 2 bits. 2 bits. 0, 0 equals 0, 0, 1 equals 1, 1, 0 equals 2, 1, 1 equals 3. So with 2 bits I can address 4 things. 1, 2, 3, 4. So we'll say he's address 0, 0, 0, 1, 1, 0.
Isn't that IP?
Nope. And then here I can say I've got 8 bits.
Think of it kind of like a street address. Only there's 4 houses on the street, and
Oh.
those are their street addresses.
Now I'm gonna let you can do. I'm gonna leave this to you to do at home to do that if you want to. But I'm gonna tell you that 8 bits will take me from 0 to 255.
Oh, so it kind of like 8-bit color or something.
Yep.
Yeah, 8-bit color will have 0 to 255 values for each color.
Oh,
Gray shade,
I've
every
done
gray
it.
shade.
A gray shade, a grayscale is 0 to 250. Well,
Yeah,
0 to 255.
Yeah.
When you talk about
color.
8-bit color was 2 bits to.
No, it's 3 of them. 8-bit color.
No. That's not 8-bit color. That's
RGB.
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 Yeah.
But each
What
of
they
those.
used to do, the original EGA, CGA,
Yeah.
those
Yeah.
25, 30 years ago, they broke this 8 bits up into red, green, blue. I think it was 2 bits of each. And then there was I don't remember what the other one was used for. It was used for something else. So you could get like a total of 16 colors. 16 colors is 8-bit color.
Okay.
So
Right.
now I can say, oh, I can go here, 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 or here, but I've got 255 addresses in each one. And then I can also put another one out here that is read/write. So we can put this other one here, this 1 bit here. So this is,
Wouldn't it be separate? Like you can't do both read and write, can it?
it's one or the other, 0 or 1.
Okay.
So read means a 1 is a read and a write is a 0. So here's a digital logic symbol, is this bar. So if I say W bar is equal to
You have enough those bursts disk made to continue.
what's the right way to do this? If I do an inverter, let me look at it this way. W in, W bar out. It's the opposite of W. It's not W, not W. So this is
Like negative.
read, not write. So the way to read this is read, not write.
Oh.
Or read, not read.
Well, you
Right.
have a choice. It's
Yeah,
read
yeah,
or
yeah.
write. So if you've got a 1, it's read, not write. If you've got a 0, it's write, not read.
Read.
Yeah.
So you were making a basic assumption when we say this, that 1s are our positive, a 1 is true and a 0 is false.
The way I've heard of it is like 0 is kind of like yes, like binary is basically a yes or no.
Yeah, usually, most cases, at least people talking, 1 is equal to yes and 0 is equal to no. You can, and that's what read not write means. But you got to be careful because there are some times when it makes sense, it's easier to do things in the negative logic sense, and you have to make sure that you do the glue around them correctly, otherwise things are all backwards.
Yes, don't do that.
Sort of. So now, if I look at this, I can address 4 different things. So I can say this is read and write, and this is my address, and this is a sub-address. So this thing has a little circuit in it right here that says, is that looking at me? Hey, that's looking at me. Now I'll pay attention to this stuff, right? And so, oh, if it's my memory, oh, you're saying to write something to me, so I'll take, then you'll say, okay, here's the data for you to write. And so now this becomes a little bit bigger, right? Now you've got your data bus here. So now let's say you've got 8 bits of data.
Which is not gonna happen.
In those microcontrollers, you shoveling 8 bits around.
No, on a computer.
Well, yeah, they just
Yeah, on
keep
a modern
adding
computer,
more
it's
bytes.
64 bits and a chunk going out.
Yeah.
So basically all the action happens in the memory, or
No,
All the
they're-
action happens right here.
Oh.
That's instructions, though. But the thing is, if you don't have any other stuff, the problem is that you can't hold a whole bunch of stuff, right?
that's what the memory is for.
No, that's yes, but you have the bus to move that information from one part to the next.
Right, so
So
here's,
you can
here's,
store it.
here's the way these things actually work inside. This is going to be transparent to you.
Right.
You're going to say, I want to add you're going to say, you're going to have so this is data memory on these guys, and over here is instruction memory. And I think this is what makes it the Harvard architecture. They're separate. And so this always feeds in here, and there's a separate address bus that comes off and talks here. So this is an instruction pointer. That's the address of the instruction. So whenever you write your code on the computer, you're going to tell your computer to put it here. You're going to say, on your Arduino, you're going to write your little code, and it's going to compile it, and it's going to stuff it out on the Arduino board. It's stuffing it there.
Oh.
This is flash. This is read-only memory, or yeah, basically it's a kind of ROM. Read-only. It's rewritable, so maybe it's a.
Yeah, but once it's in there,
Then I can walk away. I can go plug it in on another computer, and it's going to do the same thing.
yeah.
So now, what's going to happen is you're going to have a bunch of variables in there. Let's say you write a piece of code that says write 5 plus 7, right? So you're going to say, I want a variable x. In your code, you're going to write x equals 7, and then you're going to say y equals 8, and then you're going to say z equals 7 plus 8. Okay? So the first thing, what your compiler is going to do is it's going to say, it's going to come through and it's going to assign an address. It's going to say x is equal to 0001, and it's going to say y is equal to 0010, and it's going to say z equals 0011. So it's going to assign an address for every one of these variables, and they will be here. So here will be 0001, 0010, 0011, which is x, y, and z. And now when it gets to this thing, there's a whole bunch of instructions that have to happen. It's got to it's got to, down at the assembly core, at the assembly language level, it's going to say, read loosely, read 0001 X from memory. And it's going to be a combined thing, and it's going to say store it in register A, because there's going to be a couple of registers inside of here. There's going to be like maybe 2 registers, A and B. And then it's going to say, actually that would be move. So it's going to take 7 and move it over here to A. And now it's going to say move 0010, which is Y, from memory, and store it in register B. So it's going to come over here and it's going to put a 11 on the data bus. It's going to put a 0010 on the address bus. It's going to have the read flag set. So this is going to put the value in there, which is 8, on the bus, and it's going to come in here, and there's going to be internal switches to make sure that it lands there. And then it's going to come here and it's going to say add A comma B. So now there's going to be another little register here, and it's going to come in and it's going to be added, and this is going to be C, we'll say. So that's going to go straight to C, and now it's going to write
Z.
Write the value of C, which is
Z.
8 and 7,
80 pound maximum.
8, 90, 16, 15, 15 to Z. So now it's going to come over here and it's going to put a 11 on the bus, and it's going to put a 0011. It's going to put a 11, bunch of zeros followed by 11, and it's going to set the right on the address bus, and on the data bus it's going to put 15, and now Z is going to have the value of 15 in it.
That's on the memory though, right?
In the memory.
Yeah.
I think what
So-
we normally call it is
So when you said this, Z equals 7 plus 8, this is what had to happen.
Oh, so basically you added extra ones to basically Z.
no, these are all in binary.
Yeah, I know. What you said you added 2 zeros in.
Well, what it did was say it's gonna write to device 11 memory.
I misspoke a little bit. So the first thing he said is here. He said we're going to say I'm going to put on my address bus. I'm going to put a 1 1, and this is a read. So I'm going to put a 1 for read, right? Read 1 1 1 0 0 0 0 0 0 0 1. So I'm going to put this out on the address bus. So this is the address bus. And then the data bus, this guy is going to put a 7, which is 0 1 1 1. It's going to go onto the data bus, preceded by zeros. So that's 7. You can do the math later and figure that out, or do the patterns, and you'll find out that if you keep following that pattern, you get the 7. And inside, it's going to stick it in that one. And then the next thing you'll see out here, if you're monitoring all these things, is you'll see, oh, move Y, so you're going to get a 1 1 1 0 0 0 0 0 0 1 0, and on your data bus, you're going to get an 8, which is a 1 0 0 0. And then internally, it's going to do this add, and then you're going to get down, so you won't see anything on the data bus, and then you'll see this, so this will become a 0 because it's a write, 1 1, and it's going to go to Z, 0 0 0 0 0 0 0, whoops, 1 1, and on the data bus you'll see a 15, which is a 0 1 1 1 1. And that will now be there in memory. So now so this is a basic understanding of what's going on in the core when you're doing all this stuff. 5 plus 3, it's going out and doing a bunch of crap to do this. On an Atmel microcontroller, your internal clock, remember we talked about clocks before? This is the lockstep that's making everything happen. Tick, tick, tick. On a clock edge, this instruction happens.
Which the internal clock's in the computer, or
There's an oscillator.
On these microcontrollers, they have an internal oscillator that you can set up to about 16 megahertz, but usually around 8. But it's really kind of a poopy oscillator. It's not real good. It drifts back and forth and does all sorts of stuff. On the Arduino boards, there's a crystal outside and there's a crystal oscillator, and they're running at 16 megahertz, and it's pretty good. It's not great, but it's pretty good. It's like in parts per 100 million error that it drifts with temperature and whatever else. So if this is happening at 16 megahertz, which is 16 million
Times the sun, yeah. Cycles
hertz, that means this happens 16 million times cycles per second.
Does it happen at the beginning of each?
I don't know if they're positive edge or negative edge, so
Okay.
it could be on the falling edge, but I think it's on the rising edge. So every time that happens, this instruction happens, and this one, and then that. So this happened, this happened, this happened,
Is it
that happened.
Is it so that you don't, so some of the instructions doesn't get garbled or it doesn't interfere?
So
That I never knew that it happens on a
So
consistent
what's
cycle.
going on inside is when you do a logic design, they're called logic clouds, right? So let's talk about this, right? There's an add, there's some logic that does an add,
Right.
and there's some logic that does a subtract. And these things have to happen. There's other things that have to happen, right? There's a read, there's a write, there's
Sure,
and,
sure.
And so there's things that are going on.
Series of instructions.
So
Simple instructions.
What I have is I have a register that has data in, and then data comes out, and maybe it goes to all of these. And then there's a device here called a multiplexer in this particular instance that based on, this add said, oh, this is 0 and this is 1, so I said go to 0, so this path goes through, 0 makes that path happen. And then I have a register here that captures the data, and then here's data out. These registers are all tied together, and the clock is here running them,
Okay.
and that means it's an edge. So tick, tick, tick. And your fastest clock is defined by how long it takes that data to propagate through the longest signal path
Yeah.
to get here. So if I start running my clock faster and faster and faster, if I'm overclocking, there's a chance that I will get to a point where I'm not latching the data right. That the
Of course.
data isn't here yet.
And you're
It's
doing
not
something
valid.
else.
And now things get corrupted.
Okay.
so basically the sub shouldn't connect to the add. Like,
Right. This is a like a track switch on a train, right? It's this way or that way. This way or that way.
This is, well, keep in mind, this is very simple.
I
Example, right?
I'm simplifying things a lot.
Yeah.
When you start talking about your Pentium processors or whatever and
Yeah.
their pipeline architectures, now you have a data cloud and a register and a data cloud and a register, and so they've got like a 16 deep pipeline, and this one is the one that comes out here and fetches the instruction, and this one is the one that does the add, and then this one is the one that moves it back to a register,
so,
and so these are all
so basically it's core.
yeah.
So sub gets into the pipeline of add, it's corrupted.
Right, if you get too fast, you corrupt your data. It's actually true. They simplify their latches, and you can actually run too slow. And if you run too slow, on your Pentium chips, this is what's called a transparent latch. So if you if you haven't latched, if you're in the condition where you're waiting, the data can still go through. And then when you pull the
Yeah,
latch,
but isn't it just garbage?
well, what happens is this data gets to here sooner than it should have.
Yeah, what I'm
And-
saying is that, like in programming, a lot of times when you, suppose that you want an address. Like, so basically what happens is that in any type of programming is that you have an address in this memory heap. You have to have an address. And a lot of times it has a bunch of garbage in it. So every time you have...
Well, that's just the way you start out, because you don't know what's there to start.
Exactly.
But what I'm talking about is down in the instruction core, these latches, they saved...
What I'm saying is that a lot of the time in these latches, if the assignment isn't complete, it's pushing out garbage that what's already in there.
Right, but what I'm getting at is, yeah, so at the beginning, when you very first start up your computer, trash rolls through it.
Right.
It's got a bunch of stuff that, I mean,
Yeah.
they do things to keep that from happening. But having a latch that works strictly on the edge takes more transistors than one that works on this high level. So what happens is when this level is high, the data can go through, but when it goes low, it does the latch. So now it grabs the data that's there and it can't go through. So if I run this thing slower, right, so these are longer, now I've got more time for data to go through. So what I want is for the timing of this, from the time we go through here to this cloud to here, the maximum time, T max, is equal to, I don't know, let's pull a number out of it.
Yeah.
And say it's 10 seconds. We know that's not true, right?
Right.
But the shortest time through is T min, might be 1 second. So I want to time this so that, that's too gross. Let's make that 1.1 seconds. So I want this,
Still a little untrue.
it's
So-
nanoseconds,
Yes.
microseconds.
So once it finishes instruction, it just waits for the next
Yeah.
Right,
but what happens if I'm here too long and this short data makes it in and it's propagating through and I still haven't gone low
yeah,
to
you gotta
latches,
come to
then
the
it
other
comes
side.
out the back side,
Right.
and now it's managed to work its way through this, partway through this.
So it'll still go through. There isn't no physical gate.
The cloud has no gate. The latch is the gate.
Okay.
So it starts to work its way through. I latch this gate and it hasn't made it. So that tells me if this one's like a 1 second delay, and this is a 1 second delay, that means from the time to get here to here is 2 seconds. My clock has to be shorter than 2 seconds.
So
If it's longer than 2 seconds, this comes all the way through and gets latched here. And somewhere else, where it was, slightly longer, it didn't
Yeah.
get latched. So now my data's out of sync. So the whole idea of a pipeline is keep things in sync. Keep things in sync. You got a little metronome there going tick, tick,
Yeah,
tick.
but
The conductor's
But at the same time, you don't want the instruction to be too damn long.
right, right.
So
Or
the latch
too short.
But if you run it too fast, right? If I run it too fast, if I run it at a half a second,
Yeah.
now my data only makes it to there, and I've latched the old data. So it didn't make it through.
Right.
And now suddenly I've skipped a clock backwards in time,
Uh-huh.
but maybe not all of them did, and so now my data's screwed up again.
Yeah.
So the latch is open at a predetermined time.
Yeah.
Yeah.
This clock.
So
Yeah,
if you're too fast, you will crash in too fast.
Eventually you go too fast and data doesn't make it through.
Yeah.
Or
Or
the
you
other
can
way.
go too slow and
Once
data
you
makes
get-
makes it too far through.
Yeah.
Oh, I thought.
I got a sausage cutting machine.
Yeah.
Yes.
Or what is that? Lucille Ball when she's making chocolate.
Yeah.
Oh God, I don't remember. I love Lucy.
Yeah, I love Lucy and the chocolate factory.
All right.
Oh, I think we have to get out.
And this was pretty confusing since I know no basic.
Yeah. Well, so we're jumping around and I'm trying to give you a little bit of insight into what goes on in here.
So basically, you're
without killing you.
Yeah.
Right. I mean, I have a textbook at home that's this thick that's on nothing but computer architectures.
Oh,
Yeah, getting down into this was a master's level class for me that was 3.5 months. I've just condensed a big chunk of
So-
that down into.
What's for next week? Oh, wait, no class next week?
Not next
No
week.
class next week, so what I'm gonna do is I'm gonna assign a homework.
Okay.
The homework is to make a light blink at approximately 1 second on, 1 second off.
Okay.
That's what we're gonna do. So what I'm gonna do now is I'm gonna talk a little bit
Okay.
about what some of these things
I
are.
think we already done it in a previous,
We've done it, yeah, we've done it.
yeah. But we can bring it, we'll bring it in.
But
And
we
it's
don't
more-
really remember it.
But again, it's a refresher.
So the onboard LED or
No, it's yeah,
because the one on mine, there's a blink that you can do on the onboard LED that's on there.
If you can control the onboard LED separately, all by itself, that's fine. I don't care. And I'm also going to, I'm going to give you a two-part. Okay, I'm going to write it down and then I'll talk about it. Talk about what's going on here. We've got two exercises.
Okay. And was the plan to aim for 2 weeks?
2 weeks.
Okay.
So-
And so between now and 2 weeks, if you go back and watch the other 3 videos,
where can we find it?
they should be on. If you saw it on Meetup or on Facebook, they should be in the description of the event.
Okay.
Yeah.
I think I went through Meetup
Yeah.
website.
If you write down your email for me,
Okay.
I will send you the link to the
I'll
YouTube.
just is it
Yeah, that's me up there.
IT?
I.
Oh,
I'm a
I.
Roman numeral 2.
Okay.
Homework number 1. Make an LED blink at about 1 hertz.
Hertz is a second.
One time,
Once per second.
once per second.
Cycle.
So that means you'll be generating a square wave that looks like this, with this time period being 1 hertz or 1 second. So it'll go on for a half a second. So it'll go on for half a second, off for half a second, on for half a second, off for
So
half a
that's
second.
where it gets hertz.
1 per second. This is a cycle of on, off.
Okay.
Cycle per second, a hertz is the same thing. It's named after a guy named Hertz. Hertz.
What's the homework number 2?
Homework number 2, and then there's going to be an extra credit one. So we're going to, homework number 2, there's going to be a button into your microcontroller to the LED. When you push the button, the light comes on.
Oh, okay.
When you let off of the button, the light goes off. So this one is output only. This is input. This is output. Now remember what I talked about how to wire up switches, right? So this needs to either be 5 volts and ground, like this, so when you push it, it grounds it, or it needs to be horse poop. Needs to be that. A good number for this is probably 10K, and for this is probably 220 ohms. And you can get where that comes from the, I think it's last week's talk where we talked about the LEDs and how to ballast them. And 10K is because 5 volts divided by 10K is like half a milliamp. Yeah, it's about a half a milliamp. And then the extra credit, if you want to go there, is, dare I? This is real extra credit. Extra credit, yeah. Extra credit is you count the bounces.
You count the what?
The bounces. When you push the button, how many times does the microcontroller think that it actually clicked?
Oh, okay.
And so this is in last week's. There's no such thing as a perfect switch. When you push them, they don't make. When you push them, they actually, The metal
Really
comes
fast.
down and it bounces.
Okay.
It's a literal bounce. And what you see in your circuit is, this is no volts, but when I press it, it goes like this, and then when I let off, it does this. What you really see is you see something like that. You see something like this, and then you see something like that. So if you want to get really crafty, this is a really, really hard extra credit. Count how many times it thinks, and it'll be different every time. You push it once, and it'll think it only clicked it once. And you'll click it another time, and it'll think, oh, you did it 73 times. It'll never be the same twice. This is hard.
Actually, I think I know how to solve this mathematically.
But doing it in the code to tell the microcontroller to do something every time it does one of these, that's hard.
Yeah.
That's hard.
Okay.
That's actually kind of hard. I'd have to sit down and think about this for a while about how to do it.
This is cool.
All right.
Okay, thank you.
Hey, no
We'll be back
problem.
in 2 weeks.
All right.
Okay.
Hope to see you then.
Yeah. How do I exit? Oh,
The front door.
Front door's over here.
Okay.
So let's talk about the I/O on our microcontrollers. We showed you the core. One of our blocks is an I/O block. And what you have on each I/O is a 1-bit register. We talked about that. So I got data coming in. And I've got a clock. When clock happens, it latches the data. Okay. Most of them, there is some sort of a FET that also has its own data latch. No, these are all the same clock. They all work together. It looks like this. And data in, data out. And then there's some other circuitry back here on the back end to get it onto the bus the right way. Okay, so if I want to, this is my I/O block loosely. So the first thing I need to do is I need to tell the microcontroller whether this is an input or an output. And so there's some steering hardware back here that tells this what to do. If this is an input, I'm trying to remember what you get into the assembly, there's registers you set, but pin mode. Pin mode, I think, is your Arduino command, and you can tell it, I think it's in or out, or it might be input or output, or so there's constants defined already, and input means something and output means something, and when you write it in there, it'll figure it out. The next thing, so that tells you data direction. There's also, this is what's called a pull-up. If you are doing an input, I can put a pull-up on this. So, pull-up, this is a big resistor. This is like 60k ohms. So we talked about the switch, right? I can put my switch here directly to ground and not have to have a pull-up resistor out there like I drew earlier, because it's right there. And that's what this is for, is so I can put, it's called a weak pull-up. It's pulling it up but not really hard. So I can put a switch out here and get rid of external components. So, there's a separate register that you talk to do that. I think on the Arduino, if pin mode is sent to, there's also something called digital write. And then it's 0 or 1, right? These are C function, or they're Arduino functions. They're using a C derivative, or it's all C in the back end. But so if my pin mode is input and I write a 1, it turns on this weak pull up for me to use a switch. It's just enough current to barely light an LED. So if you ever notice that you're turning your LED on and off, but it's really, really dim and you can't figure out why it's so damn dim, it's because you actually put your pin mode in input and you're turning this thing on and off. And it's just enough to light it, but it's really on an input mode, so you're not really doing what you think you're doing. If you make sure that you've got your pin mode and output, that'll be a nice bright LED out there. But if you got your pin mode and output and you do this, you dead short that and you maybe burn out your driver in there. The reality is you won't on these. They're pretty robust that way. They can drive a maximum of 25 milliamps out, I think is what they're rated at. And so they've got self-limiting circuitry to keep them from burning out. And then there's a digital read. And pin number. Actually, digital write is pin value, and digital read is value. And it will, so like Z equals that. So it'll go out, it'll read it, put it in Z for you. And digital write, whatever you want the value to be.
The read wouldn't still be pin value if you get a multiple inputs, or is it?
So,
Maybe we can get into that later, I was just curious.
the Arduino's a little bit more interesting about that. I actually, I often don't, I use the Arduino, stuff when I'm playing around with simple things, but I often end up writing assembly code inside of them so that I go out and talk to whole registers at a time, right? Because there's 8 of them. So I'm actually controlling 8 at the same time, and what they're doing is, it's called abstraction. They're abstracting that out so that when I write 1, it's going out and doing them all at once. You know, it's masking them off and only changing that 1. If I say digital write 5 times, 5 of them that are right next to each other, I honestly don't know if it goes and does this one and then does that one and does that one, or if the compiler simplifies all that and says, oh, do them all at once.
Right.
I don't know. That's compiler dependent. I don't know how it does it. I've never run that experiment to see what it does, because that requires me to hook up oscilloscopes and all sorts of other fun stuff that I don't have a lot of sitting around everywhere. So,
And as long as it does what you want it to do, it's kind of irrelevant.
well, for 93.5% of what we're doing, right, it's not that time critical. It doesn't matter. So, but when you do want to write words, again, so I'm not an expert on Arduino per se. I have some experience with Atmel and PIC microcontrollers, and then just generic C code. I do most of my stuff in C anymore, or direct assembly on a microcontroller. On Arduino.cc, there's a tick at the top for reference, and you can go in and take a look there. I'm sure there's a digital byte write or Google, you can do that. So maybe that's a fourth homework to look at, is writing a whole word at a time.
Well, I was asking about the read, if it would be, if a pin in value for the read as well, since you might have multiple inputs that you could read from.
Oh, yeah, okay, yeah, you're right. So that's a pin in value also.
Yeah.
I don't know why these get harder and harder to pull off. You'd think they'd get easier and easier. Actually, it's just pin. It's pin and the value comes out.
Oh, yeah, that makes sense.
Yeah, so I'll do it that way. And we've been an hour and 15 minutes. So maybe some tiny insight into all the god-awful stuff that happens inside the machine while it's going on. And then a description of the basic I/O cell, and then a quick, from the Arduino point of view of code, and then how to do it. And then next week, 2 weeks from now, we can talk about what you guys did and show, oh, see, it works. And I will try to put one together in my copious free time also and show, see, it works. And I can share my code, and you guys can share yours, and we can just talk about what we did. And then we'll talk about whatever the next thing I think is a good thing to talk about for the thing, and we'll go on from there. And we'll do a homework based on that.
Well, you obviously go to motors after lights.
Oh, motors! I was thinking the analog to digital converters, because that's useful for like a little for your little joystick or whatever else, and so that brings some of the input in, and then from there, after lights, it's actually A to D. So the first thing you want to do is get a light.
Mm-hmm.
Once you can control a light, you're part way there.
Right.
The next thing is actually either some sort of input to show that you can make the light happen on a certain set of conditions. So that's digital, that's fairly easy. The next is maybe analog input, and then we go to PWM, I think. Because then you can make the light bright or dim.
Right.
I want a light that comes on when you scream at it.
And so I'm kind of thinking, so we're doing a light and we're doing a button, so we're doing basic I/O. I think analog I/O, there's only like 5 or 6 pins on the Arduino that are analog input capable. Then to PWM, and then we might do, well actually PWM is good for stepper motors too. So we can have some fun with that also. Wiring up a stepper and explaining how a stepper works. And then, I don't know if we want to do motors then or not. Because motors then...
I was thinking about steppers. Yeah, specifically.
Well, stepper lets you control...
Right.
Oh, a stepper motor.
Yeah, stepper motor.
So a stepper motor, I was going to use a servo.
Yep.
So do a servo first, because I can control a servo directly from. A stepper motor requires an external components, and so does a DC motor. The Arduino cannot drive them directly, so that requires you to put something else out there.
Gotcha.
So I think we'll work through some of these basic things over the next couple weeks. It'll be fairly simple. I'll give you building blocks. And then we can start to say, what do you want to control? And we can, and when I get there and we can look, and I can start looking through stuff to see, how do I control that with this thing? Because a lot of it I don't know off the top of my head, but I know some of it.
Yeah. Cool. Sounds good.
All right, so there we go. Anything? Any questions? Any comments? God, you're boring. You're right. She was like, oh, fuck this.
I'm sick. I'm not feeling good.
I'll say, I spent this past weekend in Arizona, and it was much warmer there than it was here.